Start the registration. Okay, fine.
Okay, so good evening to everybody. We have the last session of the year for this young seminar, so the Italian Society of Statistical Physics. And today we have the great pleasure to have two very good speakers. The first of them is Clarissa Lauditi. And the research interest of Clarissa lies at the intersection between statistical physics and machine learning, and more generally to optimization problems. Actually, she is postdoc in Harvard, yeah. And she did the PhD under the supervision of Riccardo Zecchina in Torino, actually. And she's the author of a relatively long list of papers for the age of research that she has. And so I think she can start to speak. And the title of the talk, you will see now. Okay, yeah, so please, Clarissa.
Hi, everyone. First of all, thanks for the invitation. So let me try to share the screen.
I think we are, yeah.
Okay, can you see it?
Yeah, so please, you can start.
Okay, thank you so much. Okay. So, so I guess today I'm going to be talking about transfer learning, so multitask learning in infinitely wide neural networks. I'm going to be talking about feature learning. And these works that I'm going to present is done in collaboration with these two amazing people, Blake Bordel, who's postdoc here at Harvard, and my PI, Cengiz Palawan. So I guess since I probably know that many people in this audience are not really familiar with machine learning literature, let me first give you an introduction about what kind of question one might be interested in as a statistical physics that approach this field. So suppose that you're given a learning task, and for a learning task, I mean, suppose that you have a data distribution. So some data, for instance, in the classical example, you have a set of images that you would like to classify, meaning assign a label to each of these images. And then you have a network, a model architecture. In this case, in the picture, you see here, I'm showing a convolutional network. So you have a bunch of convolutional layers of activities. And throughout the hand, you have a bunch of fully connected layers, which actually implements the classification. So they give you a probability of this image of belonging to each of these classes, either car, trucks, van, and so on and so forth. So I have a data distribution and model architecture, and my degrees of freedom are the weights. So I have an update rule. If I call the weights W, I know that I can update the weights through some gradient-based learning rule. So as soon as I define a loss or a cost function, this is the update rule I can study. And in principle, what I would like to track is the evolution of these parameters. So, and the kind of question I might be interested in are the following, broadly speaking. So one question might be about sample complexity, meaning how many samples do I have to see from the training data in order to be able to solve the task, meaning to be able to actually correctly classify, assign a label to each of these images. So about sample complexity. Another question might be what kind of internal representation, meaning how does do the features update throughout learning, throughout training. And another question might be how do the learning dynamics unfold over time? So am I able to kind of develop a theory that is able to track the loss at each snapshot of time? Okay. So today, the plan for today is kind of trying to tackle two subsets of these super broad questions. And I'm interested particularly in studying what kind of limits you get when you scale up either the width, and for width I mean the number of neurons you have for each layer, or the depth, the number of layers you have of your neural networks, tracking the learning dynamics, but especially how do the representation evolve throughout learning. And a second question, and I'm going to test this theory in a setting which is multitask learning, because I'm interested in trying to answer the question, which is how the learned representations in a pre-training phase gets integrated when I fine-tune a downstream task, but I will exactly define what do I mean by that. First of all, let me just give you a general remark so that we kind of like hope that we are on the same page. So a neural network can be seen, of course, as a system of n neurons interacting during training times. And as a physicist, as a statistical physicist, what one usually done in order to theoretically being able to tackle this problem, this system, is actually sending the number of neurons, or either the width or the depth in this case, to infinity. Because what you hope is that in this limit, when you use tools like dynamical mean field theory or replica methods, you get that the system really gets simplified, and you get a description where each neuron actually represents its high ID. It's an independent neuron, and it's represented by a stochastic process, which is coupled to population averages. So I asked ChatGPT to give you a sketch of what is happening here, and it was actually pretty good. So on the left, you see that you have a fully connected graph, which represents your neural network. So you have a neuron is interacting with pairwise interaction. And what has happened as soon as you send n to infinity is that these neurons, as I told you, becomes high ID, and the interactions are replaced by averages, average effects. So, but we just did a big jump in the sense that I'm saying, oh, I want to develop a theory by sending this number of neurons to infinity. So one important question one might ask is how do actually how fast, what's the rate in which you actually approach these limits? And this is exactly a question, and it's which is very relevant about scaling laws. And more precisely, in this setting, one might be interested in answering the question. Suppose that I give you a compute budget. What's the optimal way to allocate your resources in order to optimize for the test loss, for instance, right? So what's do I have to see more data? How do I scale the width or the depth? How do I scale training time, and so on and so forth, which is very relevant for practitioners. Also, as a theorist, you can ask yourself, it's this limit that you're taking, this thermodynamic limit, actually a good proxy for what a finite width and finite depth neural network actually does? And the honest answer to this question is it really depends. It depends on the parameterization, and I will be much more clear in a second. But what you can do, as it usually the case in physics, is actually computing finite width effects through perturbation theory. So what is this is just for a remark. What is the general setup we are considering here? So the setup is, suppose that I have an input, which is a d-dimensional vector. And I want this input to be mapped to an output prediction, which I call f of x, to a number L of layers. This that I'm showing, it's a multi-layer perceptron with two hidden layers, and each hidden layer has a number of neurons n. So the width is n, and I'm going to be thinking again about sending this width to infinity. So how does the input gets mapped through the output? Usually through the Sandler recursion rule. So if you call W0 the weight matrix of the first layer, basically, you multiply x through W0, and it gives you H1, which is an n-dimensional vector, because this is the pre-activation vector at the first layer. Then I have phi, which is as the rule of the nonlinearity, which is applied element-wise. I apply that to H at layer L, multiply that through WL, and it gives me the pre-activation at layer L plus 1, and so on and so forth, until I get to the readout, which gives me the prediction F. So I haven't specified already the data distribution or either the update rule we are going to be thinking of, but just in general, suppose that you're given this model architecture, you can think of training that once you have a learning problem from random initialization, such as by setting the weights at initialization as standard Gaussian. So as soon as you take the width to infinity, you see that you have a bunch of factors here, square root of d, square root of n, of course, for central limit theorem kind of reason, because you want these objects to be order 1 in the limit, right? And I'm going to be do everything like that, except from the last layer. When you see I have here a factor gamma, which actually plays a very important role. So for whoever is not really familiar with the literature, what does happen if gamma is just an order 1 quantity is that as soon as you take the width of this neural network to infinity, you recover the neural tangent kernel type of results, which basically tell you that throughout learning, the internal representation of this network will remain frozen at initialization, which means that you can linearize your predictor dynamics in a neighborhood of the initialization. So the actual network is just frozen, and what you're basically learning is just the readout. So this is an important result theoretically, but if we want to study feature learning, meaning how the features updated, how the representation evolves throughout learning, this is not a meaningful limit theoretically speaking. So in order to avoid being in this kind of regime, what we can do is actually changing parameterization, meaning allowing this factor gamma here to scale with a constant gamma 0, which is very important. It will come up multiple times throughout the talk. It's called, we call it feature learning strength, and then you have an order square root of n quantity. This is known as mean field or mu-p parameterization. And so what happens if you parameterize the network like that is that in the infinite width limit, you still get representation learning, meaning this pre-activations vector here will update in a meaningful manner, meaning in a task relevant manner, okay? So I don't have enough time to get into the details of how can one develop the theory, but as a physicist, one might care about what are the, okay, suppose that I were to study the training of this neural network in this parameterization, what is kind of like the summary statistics that you get, right? The order parameters. So, well, if you were to develop this dynamical mean field theory for infinite width, what you will see is basically that the order parameters are basically representation, in this case, representation similarity matrices or kernels. So this kernel here is phi, and it's a data by data kernel. You have multiple indices here, so let me unpack them for you. You have a layer index, so you have a kernel at each layer. Then you have a time. It's a 2-point correlation function at time t and s, and then you have a mu and nu, which are data indices. So what I'm basically doing is studying the dot product of h of these feature vectors, phi of h. Remember here from the network definition, these were actually the pre-activation vectors, right? And dimensional vectors. So phi of h evaluated the different pairs of data points. So how does the kernel look like? Well, suppose that in the simplest possible setting, you have a bunch of data, and these data are labeled either to plus or minus 1. So I have a regression problem with just 2 classes. And suppose that I reshuffle the order of these data such that I first have in the top left corner, I have all the data that belongs to plus 1 classes, and in the bottom right corner on the minus 1 classes. If I look at what this kernel is telling me as a function of feature learning strength, is that this block structure that pops out is basically telling me that the networks, as soon as I increase what we call the feature learning strength, is actually learning how to increase the correlation between data points that belong to the same class and decrease correlation between data points that belong to different classes, okay? And the lazy limit here is actually the neural tangent kernel type of results that I told you about, meaning this is the kernel at initialization and will stick like that throughout learning, because in that regime, as I told you, representations do not evolve, okay? But so you have a forward kernel in the sense that the similarity matrix per kernel. But if you were to train a neural network through gradient descent, you have a forward process, but also, of course, a backward process. And because of that, you have the equivalent for the backward dynamics, which is a gradient similarity matrix, which is basically dot product between gradient vectors. And again, mu and nu are indices that spans over the data points. So what do I mean by saying that these are the relevant summary statistics in this case? Is that these are sufficient to predict the network performance. So if I were to study F, the predictor, the dynamics of F, this will be actually a function of this phi and g at each layer, these matrices at each layer, okay? And one interesting result is that as soon as you take the time, the training time to infinity, what does actually happen in some training limits is that the predictor, half of x, at the end of training is a kernel method, meaning it has actually this form where you have a sum over the training patterns. A, mu are just coefficients scalars that depends on the training data. And then you have a dependency on this k star, where k star is a function of this phi and g, which we call adaptive kernel in the sense that differently from neuron tangent kernel type of results, it adapts again in a task meaningful matter. So what do I mean by that is that in order to find out what is this k star, you have to solve for self-consistently for these phi and g kernels, right? Okay, so this is the general picture. We have a theory that in principle tells you that the summary statistics are these adaptive kernels and what we can do with that. Let me tell you about the learning setup. So in this talk, I'm gonna be focusing, as I mentioned, on transfer learning. I guess a lot of people in machine learning believe that in 5 years or so, we will be data bottlenecked. So I think it's very useful and interesting to study transfer learning from a theoretical perspective, because transfer learning is actually a principle to escape data bottleneck. And the reason for that, or the motivation for that, is pretty simple. In the sense that suppose that you have a target task that I call T2, and in this case, this task is data poor. So when you imagine training a neural network on this task and you don't have enough data, you will probably be worried about overfitting on this task. So in order to avoid that to be the case, what you can do is actually pre-training another model on a task T1, and actually take at the end of training the features that you get from the pre-training. In that case, these are encoded through these measures, these metrics, which are the adaptive kernels, as I told you. And then you can actually use these adaptive kernels as a warm start in order to fine-tune, or actually to train the second model on the new task, okay? So the kind of question you might be interested in this realm are a question about data, meaning which properties of pre-training and downstream data distribution enable effective transfer learning, meaning this transfer proceeded, this transfer of features to have a positive impact on performance. But also you might be interested in asking a question about representation. So how does this learn representation from pre-training gets integrated during transfer learning? And also, you know that we have this feature learning strength parameter that we can tune. So you can ask, what is the game here? The interplay between this feature learning strength and the source task alignment. So before telling you something, and maybe some experiments and the more general way in which we develop the theory, but we can kind of like develop some toy models to get really some intuition about what is happening here. Some extreme cases. The first case, oh yeah, sorry. Let me first clarify the setup, right? So the setup is again, as I told you, you have a multi-layer perceptor, and then what you want to do is actually pre-training. This theta1 is the collection of my network parameters on a task T1. which has a number of P1 input-output pairs when the data is X and the output is Y. I want to train this network, so this θ1 collection of parameters with gradient descent from random initialization. I have dynamical mean field theory, which actually allows me to compute the loss at each snapshot of time. And I have this parameter here, gamma, which was called before gamma 1 because it refers to task 1, which actually tunes the feature learning strength on my richness on the pre-training phase. And the end of training, as I told you, I can use θ1 as an initialization and run gradient descent on another task, which I call T2, with number P2 of data, for another model. So what I ultimately care about is the performance on the second task, okay? And I can imagine to be in an extreme case where actually, which is called lazy learning on T2, where actually what I do while transferring the feature is just fixing them when I fine-tune the model and just learning the readouts. This is actually obtained by sending this gamma 2 parameter to 0. I can be more explicit offline if you care about that for sure. Okay, so suppose in the extreme scenario that your pre-training model is really data rich in the sense that you have infinite data and you're taking a deep linear multi-layer perceptron and solving a linear regression problem with that. So the type of kernel, the type of adaptive neural tangent kernel that you get after learning such a regression problem is actually this K matrix, which has again a layer dependency. X is the data, and then you have basically the identity, which depends from how you initialize the bulk, from how you initialize the network. And then you see here that you have a rank 1 spike, which is in the source vector direction. So since I'm solving a linear regression problem, the useful direction, meaning the teacher is just a d-dimensional vector. So you see here that actually what feature learning is doing is creating a rank 1 spike, which has the intensity that depends on this chi-hel parameter, which strictly increases with the feature learning strength gamma 1 that you used during pre-training. Okay, so this is the shape of the adaptive kernel. What we can do with that is actually use these adaptive kernels, as I mentioned, as a fixed representation and fine-tune on another target task T2. Okay, so what we can do with that? Suppose that this second task as a number of parameter, which is a number of data, which is P2, and this is the input dimension. So in U2, we call it the duration between data and the input dimension. What you can study is actually the task loss after transfer learning. So in the transfer learning setting, my target vector is actually a level. I suppose to have a level of alignment or a cosine similarity that I call alpha. And what I'm plotting here is actually the loss, the task loss, as a function of nu2, which is the amount of data I'm seeing. So the dashed black line is actually the task loss from no pre-training, meaning I'm not using any transfer learning at all, so I'm not fixing the hidden representation to be the ones that the adaptive neural tangent kernel give me, but just to be the ones that I get from random initialization. And you see that I have a given task loss, which goes as 1 over nu2 because it's a linear regression problem. What does happen here, and all the full curves, is that as soon as I use transfer learning, meaning I fine-tune on this cast from this adaptive neural tangent kernel, I do get a benefit in the task loss, of course, and this benefit is as big as possible as soon as I'm increasing, of course, the level of alignment between these two vectors. So we can demonstrate theoretically that basically this fine-tuned loss is it's always lower of this random initialization loss as soon as this alpha here, this alignment is greater than 0. And this is precise and exact in this limit. So having a very rich pre-training source always gives you a positive effect on transfer learning. Fine-tuning is always a good thing. But in principle, in real life, you don't have infinite data. You're basically data limited. So we can study another kind of like, let's try to break this, and let's actually try to look at a more realistic scenario, which is pre-training with some limited data. So in this case, pre-training on a task T1 gives you a kernel, an adaptive kernel again, that is actually something similar to what I shown you before, but with some new terms. So you have your usual rank 1 spike in the signal direction, but now you have a bunch of noise direction, and this noise, which we call the G noise, actually captures the fact that you have finite sample fluctuation on the T1 dataset. You're really data limited. And this noise and this signal are actually uncorrelated. So in order to discover, in this case, whether fine-tuning has a positive effect on downstream task really depends on signal-to-noise arguments. So what do I mean by that? Is that if you were to study the loss in this case as a function of this number of data on the second task, you see here that when I don't have enough data, the best I can do is actually using this fine-tuning protocol. I can use this adaptive kernel from pre-training, but as soon as I have enough data on the second task, as it is reasonable to assume what does happen is that actually using fine-tuning hurt me, and it's better to learn the model from scratch, because you see that this fur curves here goes above the baseline, which is again the no pre-training curve. And another limiting case that we can study that maybe is relevant for to say something that might be interesting for practitioners is imagining that you have a pre-training which is very rich, and in this case, meaning that you have this gamma 1 parameter that is very large, eventually infinity. So what does happen in this case is that if you pre-train a network with this gamma 1, which is very large, actually at the end of the training, you will get an adaptive kernel that is low rank. So you lost the bulk, and what you get is this bunch of low rank spikes. So and in this case, in this case, you can learn a noiseless target, meaning this kind of like vector that we call beta target, just if and only if this beta target lies in the span or of these two vectors. So this is actually very bad for transfer learning. What it's telling you is you basically overcommit on the features on pre-training, and you don't get any advantage, meaning all these curves lie above the no pre-training. The best you can do is actually learning from scratch. This is not useful at all. Okay. So what we can do with this toy model is actually trying to see if they tell you something which is relevant for a more realistic setting when you train a neural network on some, I don't know, regression task. Okay. So this if we were to plot the loss of this toy model as a function of P2, and this is a neat map because we are changing the kind of like the richness, as I just told you on the first task. This is a summary of what I told you, in the sense that as soon as you don't have enough data on your actually target task, the best you can do is actually increasing this feature learning strength, this gamma 1. But as soon as you have enough data,
yeah.
What, sorry?
Check the time, 2 other minutes, please. Yeah.
Okay. Yeah. I'm about to. I have 3 slides left. Yeah. What is happening here is basically that the best you can do, you have an optimal gamma. The best you can do is not actually taking a gamma 1 as large as possible, and this is actually what happens in real life. I'm here. I'm showing it's a multi-layer perceptron. I pre-train on 2 classes of cipher, and then I fine tune on another 2 classes of cipher. So when P2 is actually small, the best you can do in order to improve the test loss is improving this gamma 1 parameter on pre-training. But as soon as you increase P2, actually these curves collapse and a different gamma 1, so you lose any advantage of having a rich pre-training course, and eventually this curve crosses, as it is for the toy models, meaning that actually you have an optimal gamma 1 in which you can pre-train the network. We can in principle develop theories in a more realistic setting, meaning for multi-layer architecture, when you actually don't assume anything about the data distributions, or you have really complicated equations to solve. And in this case, basically, when you allow also the second task to be reached, what you can do is developing some toy setting in which you basically your task, your pre-training, maybe it's an easy task and you want to transfer the features that you learn from an easy task to an hard task, and easy and hard is really well defined in this case, because you know that neural networks learn eigenfunctions in order of decreasing eigenvalues, right? So we can change kind of like the degree of Hermite polynomials if I were to set up a task. So, and here I'm showing the performance of having no pre-training, the task less as a function of Steph for different gamma 2, which is the feature learning on second task. This is actually the performance using transfer learning. So it's really gets me a benefit when I move from easy to hard. It's not the case if I move from a hard task to an easy task. You see that these curves are actually basically the same. You don't get any advantage from transfer learning. And the idea of that is that these high degree freezers in this hard task force the network to rely on these high frequency components, which are not needed to solve a much easy task. So it's better to learn actually from scratch. Okay. And we can also test it on more realistic data sets, again, maybe on NIST or on Cypher10. So you have that, we have this theory through DMFT that actually allows us to study the task loss in these two cases, so no pre-training versus transfer learning. And you see here that the effect combined of having transfer learning and also being rich, doing feature learning on the second task really helps you in order to optimize the performance compared to the previous setting. So to conclude, since I'm a bit out of time, I guess. So what we talk about are there are some interesting limits in which neural network at infinite weights behave like these kernel methods, with these adaptive kernels, the summary statistics that are task dependent. And there are some theoretical analysis that you can do in multitask learning and transfer learning setting for these wide neural networks, where these kernels depends on both tasks, pre-training and transfer. So you can ask yourself questions like about the data, about how the internal representations evolve throughout in moving from one task to another, and so on and so forth. So thank you for the attention. If you have any question, please. I'd be happy to answer.
Yeah, please. Thank you very much, Clarissa. Please ask if you have questions. Yeah. Lucilla, please.
Thank you, Clarissa, for a very clear talk, a very interesting subject. I was wondering, do you have an idea how your result would depend if you change the structure of the hidden layer? So instead of having a perceptron with a fully connected hidden layers, you have a complex network like a small world or a scale-free network. How your loss function would depend on that.
I guess so. You can develop the theory, and I talked mainly about fully connected networks, but we have the theory for convolutional architectures also. So I guess, and the picture doesn't change in the sense that the relevant things you might care about in the settings are actually the amount of data on the transfer learning task, and actually this parameter here, this feature learning strength that you can change in both pre-training phase and transfer learning phase. So I guess you have many hyperparameters that you can tune, and so the picture is very complicated, but there are some intuition you can get in the sense that still remains true. For instance, the fact that when you have a very rich pre-training, meaning that you send this gamma 1 parameter to infinity, really you get a low dimensional kernel. Even for convolutional architecture, this is true, and so this might be actually detrimental for your performance in a transfer learning task. So in some limits, you can get some intuition about what is happening that is consistent across architectures.
Okay, thank you.
Okay. Okay. Are there other questions? There is time maybe for a short question. I don't see, so I think we thank again Clarissa. Yeah, and thank you very much, Clarissa, again. And I'm going to introduce the next speaker of today. He is Carlo Vanoni, and let me tell you a few words about him. He obtained the bachelor and the master degree in physics in Milan at University degli Studi di Milano with Sergio Caracciolo. Then he moved to SIFS and obtained the